Good morning. Welcome. We're starting our series on the lectures on the sun, so this will be lecture number 1. The sun. And we're going to be addressing what is the structure of the sun. And sunspots. And what about sunspots? And what about sunspots? Cause, structure. Let's start with a cutaway view of the sun. Try to keep up with me and as accurate as you can in the scale that I'm about to draw. I'm going to try to do a good job for you. So here's a cutaway sketch. And let me start by drawing a sun. Again, please try to do it kind of in the scale I'm about to draw it. Something like that. And I do a cutaway of the sun this way, like that. Then in the middle we should draw the core, something like that. Something like that. And I have both the convective zone and the radiative zone, so we need one more layer to kind of identify here like that. Something like that. And let's see which one is easier. Let me do the convective zone. In this zone is when you have the convection cells going around. Something like that. Okay, not too bad, I hope. There we go. And then in the radiative zone, you have movement in this fashion. Like that. And then of course you have the core right here in the middle. Like that. Now let's label it. Let me do a little bit of drawing first. I'll put some color for the chromosphere, the lower surface of the atmosphere of the sun, called chromosphere. We see it in a full eclipse, solar eclipse. It's got a pinkish tint to it, something like that. Then the photosphere, the surface of the sun, just kind of quickly color it, color orange like this. Something like that. And let's start labeling it. I'm going to use a different color. So this is called the convection zone. Convection zone. This right here is the radiative zone. Radiative zone. The surface is the photosphere. the photosphere, and the outside lower atmosphere is the chromosphere. And let's see, let me put it here. Chromosphere, and that would be the pinkish area, chromosphere. And then of course the core in the middle. So let me do it this way, core, like that. How's that? Okay, a couple of other things. We need to do the corona yet. So what I'm going to be doing is drawing the corona on the upper atmosphere, kind of on the outside of the sun, like this. Something like that, and that would be the corona. Now I'm going to go ahead and use red to indicate some of the temperatures. So the corona is approximately temperature, approximately 2 million degrees Kelvin. The core is about temperature approximately 15 million degrees Kelvin, and the photosphere temperature is approximately 6,000 degrees Kelvin. Okay, now in terms of coloring, I'm going to go ahead and color the radiative zone in a yellowish color. I don't know why. Okay, and I'll leave the core white, if you will. Okay, there's a sketch of the sun. You should be pretty familiar with this as we go through the unit. Now, what we're going to do next is I'm going to do a cutaway of the sun, but half of it, so I need to show you both the temperature as it varies from the core to the outside, as well as the density of the sun. So of course you can stop and take your time to be able to copy this down, but let's continue underneath it. So I'm going to just draw underneath a half-away cutaway of the sun. So let me try to do as good a job as I can. This is half of the sun, if you will. I'm going to go ahead and from the middle, I'm going to just sketch it. You can use a ruler if you want to. So from that point, and I'm going to draw a vertical line, and this is the core, and this is the radiative zone, and the convective zone. Like that. How's that? Yeah, that's the best. So if you have at a point 0 right here in terms of temperature, you have at the very core the temperature would end up, let me draw it in red. So the way the temperature goes is something like that. Something like that. And it is 15 million degrees Kelvin. This is temperature, of course, on this side. Temperature 15 million. And then on the outside of the core, approximately right there, you would have 9 million degrees Kelvin. In the middle of the radiative zone, about 5 million. And then it drops drastically to 6,000 degrees Kelvin at the photosphere. Okay, in between it's like 3 million, but 3 million and then 1.4 million just following the curve. We'll do that, this curve a little bit. Right there like that. So that should give you an idea of the temperature from the core to the outside. And then of course you realize that the temperature as it goes into the corona, it gets up to 2 million degrees Kelvin. So that's what it's looking like. Now that's temperature on one side. On the left hand side we have density. I'm going to go ahead and draw density on this side, and in a similar fashion, but I want to make sure you guys understood how dense the core is. I'm going to go ahead and draw a graph like that. So this is kind of like dividing line. On the right hand side is temperature, and on the left hand side is density. So we go from a density of less than 1. Near the surface is 0.08. Now this one will be in grams per cc. The temperature here is Kelvin. The density would be in grams per cc per cubic centimeter. So don't forget to write the units. But it goes to the core to 160 grams per cc at the core. That's pretty dense. Then you go through an iteration as you go through from like 4.0, still in the convective zone, to like 34 as you approach the core, and then down to 160. Just for comparison's sakes, underneath it, okay, very, very extremely dense at the core, then less than 1 at the surface. But just for comparison's sakes, let's look at the density on Earth of some of the chemicals. Density of gold, which is pretty heavy, Au, is approximately 19.32 grams per cc. The densest metal that we have in our periodic table is osmium, this element osmium. Symbol is OS, is approximately 22.59. This is similar to titanium. So it's extremely dense, so 22.59, and look at the sun's core is 160. I needed to make sure that you understood that. Okay, make sure that you catch up, and you can pretty it and color it as you need to. But let me go to the back and talk a little bit about sunspots, give you some information on it, and then we'll wrap up the lecture. So in the back, let me continue. And you have sunspots. Okay, on the left-hand side, let me do a very quick sketch for you. You've seen the sunspots. Here is in the sketch, quasi-circular type images. One of these is approximately Earth size, so realize that the Earth is about as big as that. It varies, obviously, but just for scale sakes. Now, they give it a name, although there's no shadows involved at all. They use some of the shadow names to call the darker spot umbra. And on the outside of it would be less dark, if you will, in this area right here. They call it penumbra. This area right here. So on the inside, umbra and penumbra. Now, this is, don't forget the Earth, just for comparison. Now, the sunspots are the dark, in quotes, dark areas on the sun's surface. And they are linked to the sun's magnetic field. Okay, they are cooler areas by about 2,000 degrees less than the photosphere, about 4,200 degrees Kelvin versus the photosphere, approximately 6,000 degrees Kelvin. Important in this, they're on 11-year cycles. At maximum, there's approximately 100 spots, 100 to 150 spots. At minimum, only a few. At minimum, only a few. Okay? So the 11-year cycle, if you were to draw it in this case, I'm going to go from 1995 and let's draw 2000. Let's do 2005, 2010, 2015, and the predictive in 2020. You would end up basically going from 95 to a high in 2000, like this, to a low, to a high, and now we're approaching a low. So it would be something like that, approximately 11-year cycles, and here's about 100 spots. So this is number of spots versus years. You'll see this bit more detail later on as we go through an 11-year cycle. So try to sketch it as best as you can. And this is cycle 23. And this is cycle 24 right now, from the time we started counting. These are the cycles. Now, just to make sure that you understand how important the sun is to our planet, just that there is a time in which the Maunder minimum from 1645 to 1715, there were very few sunspots. It's called Maunder minimum. From 1645 to 1715. It corresponds to the Earth's little ice age, which happened from 1500s all the way to 1850. Okay. This should tell you that basically solar activity and Earth's temperature are linked. Further study needs in this area, but let's see. The last thing I have for sunspots is the streams above a sunspot are magnetic fields. So the streams above sunspots are linked to magnetic fields. And the active regions above the sunspot can be seen in the chromosphere and the corona. So if I was to draw the surface of the sun, something like that, and this is a sunspot like that, basically you will see the streams slightly above the sunspot, and some of them will extend into the corona itself. So they look like arches. You've seen images of that in some of the videos we've seen. So, okay, something like that. How's that? Okay. Thank you so much. That will be the end of lecture number 1, and we'll continue with our unit as we move on. Thank you much.